In this video, we solve an integrodifferential equation using the Laplace transformation method. This is problem number 3 from quiz number 8 in the fall 2020 semester in our elementary differential equations class. Integral equations and integrodifferential equations are associated with standard L28. So we have this integrodifferential equation. We start by letting the Laplace transform of y equal big Y of s. So everyone knows what our notation means. And then we take the Laplace transform of both sides of the differential equation. When I see this integral, the first thing I think of is a convolution between two functions. So I just need to identify the functions. Oops. Let's get a red marker. This is f of t. And this is g of, or f of tau, and g of t minus tau. This is the convolution of f with g. So the whole thing is the convolution, in this case, of y with cosine of t. Now that's not a regular product, that's a convolution. A convolution is a special product, which is the integral from 0 to tau, or excuse me, from 0 to t of f of tau times g of t minus tau d tau. There's no d tau there, there should be a d tau. Okay, so when I'm evaluating this, I just use my properties. The Laplace transform of y prime is s times y of s minus little y at 0. Then I have the Laplace transform of cosine of t. It's cosine of kt, where k is equal to 1. So that's going to be s over s squared plus k squared, so it's s squared plus 1. And over here we have the Laplace transform of y, or the convolution of y with cosine of t. That's the Laplace transform of y times the Laplace transform of cosine of t from our theorem. Now, y of 0 was given in the initial condition to be 0. So we have this. S times y of s equals s over s squared plus 1 plus the Laplace transform of y, which is y of s, times the Laplace transform of cosine of t, which is s over s squared plus 1. Now we want to get y of s by itself. So I would subtract this term from both sides. And I think I'll factor out the y of s as well. So I've got s over an implied 1 minus s over s squared plus 1 equals this s over s squared plus 1 over here. And I need a common denominator. So I'm going to multiply this by s squared plus 1 over s squared plus 1. So that gives me this y of s times s cubed plus s minus s all over s squared plus 1. That's convenient. The s's reduce. And if we want to get y of s by itself, we'll just multiply both sides by the reciprocal of this guy. So we'll have s over s squared plus 1 times the reciprocal of this, which is s squared plus 1 over s cubed. Then the s squared plus 1 reduce, and we end up with 1 over, or an s over s cubed, which is the same as 1 over s squared. And that means the y of t is the inverse transform of 1 over s squared, which is just t. Easy breezy. Now, if you're saying, how do we check this? Well, you can replace y with t up here and show that this all actually gives us the correct result. When t equals 0, so the initial condition is obviously satisfied, then the integrodifferential equation, we're just going to check. We don't have to check, but we can check. The integrodifferential equation is y prime equals cosine of t plus the integral from 0 to t of y of tau times cosine of t minus tau d tau. Okay, well, if y of t is equal to t, y prime of t is equal to 1. So the left-hand side of this differential equation is just 1. The claim is that the right-hand side is also 1. So let's evaluate the right-hand side. Right-hand side is cosine of t plus the integral from 0 to t of y of tau. So I'm replacing t with tau here. So this is tau times cosine of t minus tau d tau. Well, for this I would use integration by parts. Let u equal tau. dv would be everything else. Since u is a polynomial, I'll take the derivative until I get 0. dv is that cosine of t minus tau. We're anti-differentiating with respect to tau, remember. The antiderivative of cosine is sine, but I have a -1 inside, so we have to multiply by a -1 as well. If I'm taking the derivative of this with respect to tau, I get negative cosine of t minus tau times a -1. The negative times a negative gives me the positive cosine. Okay, then we take the antiderivative of this. The antiderivative of negative sine is cosine. But I need another -1 because of that negative tau as well. So let's take derivatives and check. Derivative of negative cosine of t minus tau is a negative sine of t minus tau times the derivative of the inside, which is giving us a negative sine of t minus tau. And then the derivative of this is negative cosine of t minus tau times -1, which gives us a positive cosine. Good. So according to integration by parts, tabular integration by parts, we just multiply across these diagonals and add. So we do this times this plus this times -1, and then we evaluate from 0 to t. So we have cosine of t or plus t negative tau, times sine of t minus tau minus a negative cosine. So it's going to be plus cosine of t minus tau. Evaluated from tau equals 0 to tau equals t. When tau equals t, we get -t sine of t minus t plus cosine of t minus t. So this is sine of 0, which is 0, and this is cosine of 0, which is 1. And when tau equals 0, we have 0 plus cosine of t. So we're subtracting all of this evaluated at 0. So we're subtracting 0 plus cosine of t. So we end up with cosine of t plus 1 minus cosine of t is equal to 1. Therefore, the left-hand side equals the right-hand side. So this function, y of t equals t, satisfies the Integrodifferential equation, and it satisfies the initial condition y of 0 does equal 0.